3.2 is solving quadratic equations by factoring. Now, first, clear up a little bit of terminology. Why do we call these equations quadratic equations? Because the quad part sometimes makes students think of 4 when these are really polynomial equations of second degree. And when we see higher degree polynomial equations like third and fourth degree, once we get to fourth degree, we don't call them quadratic, we call them quartic. So why quadratic? Quadratus is the Latin word for square, and these equations first arose in looking at equations related to squares, where the side of the square was a binomial. So if you can imagine squaring a binomial like x plus 2, you end up with a polynomial equation of second degree, and if you set that area equal to a number, you have a quadratic equation. These were first explored or compiled into a work by an Italian mathematician, Girolamo Cardano, in 1545. So these are really old, and all the academic work back then was done in Latin. Cardano, interestingly, was the first mathematician to routinely use negative numbers and also acknowledged the existence of imaginary numbers. Okay, so what is a quadratic equation? It's really any equation that can be written in the form ax squared plus by plus c, where a is not equal to 0. Now, all that means, if you think about it, is there has to be an x squared term floating around somewhere. If a is 0, there's no x squared term, and you just end up with by plus c equal to 0, which is just a linear equation. Now, you've had lots and lots of practice solving linear equations. And unfortunately, for the most part, all the methods you learned to solve linear equations are not going to help you very much with quadratic equations. In general, if you had a linear equation in x, you would get everything involving x on one side. In other words, you'd collect all the terms involving x. You'd get everything else on the other side, and then you would divide by the coefficient. You can't do that with quadratic equations. To solve quadratic equations, we're going to learn a couple of different methods, and the first method we're going to look at is solving them by factoring. And it relies very heavily on a particular property that the book calls the zero product property. So what is the zero product property? The zero product property says that if you have the product of two numbers, let's say a and b, and the product is equal to 0, that implies that either a is equal to 0 or b is equal to 0. And that's really quite impressive if you think about it. You're narrowing down the possibilities from an infinite number of possibilities for a or b to a single possibility. And one or the other must be true. They could both be equal to 0. Now, contrast that with, let's say, having the product of two numbers equal 10. Really, the two numbers could be anything. There's no limitation. They could be integers or non-integers. They could be positive or negative. The only thing you can rule out is 0. In other words, you go from an infinite number of possibilities to an infinite number minus 1 possibilities, which really means you haven't narrowed it down at all. So the first thing that we have to realize is we have to try to get to a state in our equation where we have 0 on one side and a product on the other side. So let's start with an example, because I think this will become a lot more clear when we can see some examples. So here's a fairly straightforward quadratic equation. X squared minus 2x minus 15 is equal to 0. So already one of the two things that I mentioned we're looking for is true. We have everything on one side, and we have 0 on the right-hand side. So now what we'd like to do is have the left-hand side be a product. Now, turning something into a product is really just another way of saying factoring, and that's why we spent all of 3.1 reviewing our factoring methods. So we need to take that trinomial on the left and factor it. To do so, we're looking for two numbers with a product of negative 15, a sum of negative 2. Those two numbers are 3 and negative 5, so we can factor this as x plus 3x minus 5. And now we can think of the binomials as our two numbers. So we have this product of one binomial and another binomial equal to 0. So therefore we can state with certainty that either x plus 3 is equal to 0 or x minus 5 is equal to 0. Now, at this stage, notice what we've done. We've turned this polynomial equation in second degree, one with x squareds floating around, into two very simple linear equations. And now we can apply everything we know about linear equations to these. In order to solve x plus 3 equals 0, we just need to subtract 3 from both sides, and we get x equal to negative 3. In order to solve x minus 5 equal to 0, we just need to add 5 to both sides, and we get x equal to 5. And so we have two distinct solutions. The solutions to an equation are called roots. So we have two roots here. And the instructions here would have been to solve. And when you are solving, what you're really trying to do is find all values of the variable that make the original statement true. So it's very easy to check whether or not these are truly the solutions. We just have to take the two values and plug them in separately. So for instance, if we take negative 3 and plug it into the original equation, we get negative 3 squared, which is positive 9, minus 2 times negative 3, which is minus negative 6, or in other words, plus 6. So we have positive 9 plus 6, which is 15, minus 15. So the left-hand side is 0, the right-hand side is 0. It's a true statement. You can do the same with 5. 5 squared is 25. Minus 2 times 5, so that's minus 10. 25 minus 10 is 15. 15 minus 15 is 0. So again, the left-hand side is 0 and the right-hand side is 0. Now, quadratic equations, you could say that quadratic equations will always have two roots, two solutions. However, as we're going to see a little later on, there's some exceptions to that. Sometimes the two roots or two solutions are the same, and so you can either say there are two identical solutions or one distinct solution. And sometimes the two solutions are not real, and so we could say there are no real solutions. So if we limit ourselves to real numbers, if you like, you can say there's either 0, 1, or 2 roots. Never more than 2, though. Let's take a look at another example. In this case, the instructions are solve, and on the left-hand side we have 2x plus 3 times x minus 3 equal to negative 10. Now, on the left-hand side, it's already factored, which looks good at first until we realize the right-hand side is negative 10. We need to have a product equal to 0. So really, this product doesn't really help us too much. We need to bring the negative 10 over to the left, and once we do that, it's no longer a product on the left-hand side. It would be something times something plus 10, and that doesn't work. So we actually have quite a bit of work to do here. We have to expand the left-hand side. If you use FOIL, you get 2x squared minus 6x plus 3x minus 9. And we can collect everything, bring the 10 over to the right-hand side, to the left-hand side, and you end up with 2x squared minus 3x plus 1 equal to 0. Alright, now we can try factoring this, and if you have to, you can do it off to the side. It does factor. This is a pretty good candidate for the guess and check method, but you can also use the other method for factoring a trinomial with a leading coefficient. And it factors as 2x minus 1 and x minus 1. Okay, so now we have a product of two binomials equal to 0, so therefore one of the binomials is equal to 0, or the other one is equal to 0. So either 2x minus 1 is equal to 0, or x minus 1 is equal to 0. Now, if 2x minus 1 is equal to 0, how do you solve that linear equation? First thing you do is you add 1 to both sides, and then you divide both sides by 2, and you get x equal to half. The second one's much easier. Just add 1 to both sides, and you get x equal to 1. So there we have our two distinct roots. It's obviously a little easier to check the second root there, x equal to 1. Let's try it. When you plug it in, the first binomial becomes 2 plus 3, which is 5. The second binomial becomes 1 minus 3, which is negative 2, and 5 times negative 2 is negative 10. Let's try plugging in a half. 2 times a half plus 3 is 1 plus 3, which is 4. And a half minus 3 is negative 2 and a half. So 4 times negative 2 and a half is also equal to negative 10, and so the left-hand side equals the right-hand side. All right, let's take a look at a different example. Flip onto a new page. Let's say we have solved the following quadratic equation. 5x squared plus 105 equals 50x. Now, as tempting as it is, you can't solve this using the methods you would with linear equations. So don't simply try to put the x squareds on one side, the x's on the other, and then somehow divide through, because it's not going to work. Get everything on to one side. So we'll leave the 5x squared where it is. We'll subtract 50x from both sides, and we have the 105 on the left. And now that's our first step. Get everything onto one side, have 0 on the other side. Then try to factor that. Now, the first thing you should do when you're factoring anything is look for a common factor to make your life easier. This does have a common factor of 5, leaving you with x squared minus 10x plus 21. And that's a fairly straightforward trinomial, and you can factor it by looking for two numbers with a product of 21 and a sum of negative 10. Those two numbers are minus 3 and minus 7. And you still have the 5 out front. So one way to look at this is you now have a product of three numbers that's equal to 0. So when you're looking at those three different factors, you say, well, either of the binomials could be 0, but the 5 is 5. It can't be 0. And so, in essence, we ignore the 5 because we know that it's not 0. So therefore, one of the binomials is 0. And like with the other equations, we can write x minus 3 is 0, or x minus 7 is 0. And this means that x is either 3 or 7. And there are two distinct roots. Okay, let's look at another example. I'll put it up here. 6x squared plus 5 is equal to 18x plus 5. So again, first thing, get everything onto one side. So if we bring everything over to the left-hand side, you usually want to collect the terms on the side that give you a positive coefficient for x squared. That makes life a bit easier when you're going to factor it. So the 6x squared, that's positive. We'll leave that there. We'll subtract 18x from both sides. And we'll subtract 5 from both sides, which basically causes the 5's to disappear. Okay, so now we only have the two terms, easy to factor because we're just looking for a common factor. That common factor is 6x. And that leaves you with x minus 3. And again, you can think of this as two factors, product of which is 0. So either 6x is 0, which really just means that x is 0, or x minus 3 is 0, which just means that x is 3. And again, easy enough to check this. If you plug in 0, you get 5 on the left, 5 on the right, equal. Therefore, that's a perfectly valid root. If you plug in 3, you get 6 times 9. That's 54 plus 5, which is 59. So the left-hand side is 59. On the right, you get 18 times 3 plus 5, which is 54 plus 5. And that's also 59. All right, let's look at two more examples. We've seen radical equations before, and this one is a little bit more complicated than the ones you saw in the previous chapter because it leads to a quadratic equation. So the first thing you want to do is get the radical on its own. We'll do that by subtracting 7 from both sides. So the right-hand side is now x minus 7. And if we square both sides, now the left-hand side becomes x plus 5. The right-hand side is the square of the binomial x minus 7, which is x squared minus 14x plus 49. Alright, so now this sort of looks like some of the other equations on this page, and we need to get everything onto one side and have 0 on the other side, so it makes sense to collect everything on the right hand side. There's already an x squared there. We can subtract x from both sides, which gives us minus 15x, and we can subtract 5 from both sides, which gives us plus 44, not minus 44, plus 44. So now we're looking for two numbers with a product of 44 and a sum of negative 15. That's fairly easy. It's just 4 and 11. So we have x minus 4 and x minus 11. And therefore x minus 4 is 0, or x minus 11 is 0, which leads to two roots, x equal to 4 or x equal to 11. Now, those are the two roots for the equation that starts at that point there, x plus 5 equal to x squared minus 14x plus 49. And you can check it. You can plug in 4, you get 9 on the left, 9 on the right, or if you plug in 11, you get 16 on the left and 16 on the right. However, this started off 2 lines earlier as a radical equation. And so if you plug in 4 to the radical equation, you get the square root of 4 plus 5. So that's the square root of 9, which is 3. 3 plus 7, the left-hand side becomes 10. The right-hand side becomes 4. That's not true. So this is an extraneous root. Normally, quadratic equations do not have extraneous roots, but as again, this started off as a radical equation, and so like all radical equations, it can have an extraneous root. If you plug in 11, you see that the left-hand side becomes root 11 plus 5, that's root 16, or 4. 4 plus 7 is 11, so the left-hand side's 11 and the right-hand side's 11, so this is a perfectly valid root. So this is the only valid root for the original radical equation. Okay, let's see one example of a word problem. That was 5, so this will be 6. How about the sum of a number and the square of the same number? Is 56. What are all the possibilities of the number, or all the possible values of the number? Having trouble spelling possible here. Alright, what are all the possible values of the number? Now, some of these are easy enough you can reason them out. However, usually it's easy to reason out one solution, not so easy to reason out the other solution. So let's see what the equation looks like. The sum of a number, x, and the square of the same number, x squared, is equal to 56. So this is clearly a quadratic equation. Let's get everything onto one side, the left-hand side, and let's put it in the correct order. So we'll put the x squared term first, then we have the x, and then we subtract 56 from both sides. So to factor this, we're looking for two numbers with a product of negative 56 and a sum of 1. So that is plus 8 and minus 7. So we have x plus 8 and x minus 7 equal to 0. So x plus 8 is 0, or x minus 7 is 0. And x plus 8 equals 0 leads to the root of x equal to negative 8. X minus 7 equals 0 leads to the root of x equal to 7. So certainly 7 would not have been a difficult one to come up with. 7 squared is 49, plus 7 gives you 56. But negative 8 would probably not pop into your head too quickly. Negative 8 squared is positive 64, minus 8 gives you 56. Now, there's lots more interesting word problems that arise or that lead to quadratic equations, and we'll explore some of them. You can see some of them in the book, and I'll give you some examples in class.